Hi, I'm Dr. Tim Komar, and today we will show an example of solving a first-order linear differential equation using the method of integrating factors. This is typically found at the beginning of a first course in differential equations. A first-order linear differential equation can be written in this form here, where P of t, Q of t, and G of t are functions of the independent variable t, and y is the function for which we want to be able to solve. It is typically convenient to write the equation in this nice form over here, where the coefficient of the derivative of y is just 1, where again that p and g here are going to be functions of t. And of course, this equation can be obtained from this top equation over here by dividing through by P of t, as long as P of t is not equal to 0. So here's our example now. We're going to solve the following differential equation. So here we have t times y prime plus 3y equals t to the negative 1 times e to the negative t. And again, we're only going to be solving here for t greater than or equal to 0, because as we see, as soon as we rewrite this, we're going to see that our domain cannot contain 0 over here. So our first step is to rewrite the equation so that the coefficient of the y prime is 1. And notice over here that we have that t in the denominator now. Yeah, 0 is certainly not in the domain of this particular function over here. So we need to restrict accordingly. Our game now is to find the integrating factor for this equation. In general, the integrating factor is given by the following here. So it's usually represented by mu. So mu of t is going to be the exponential function e raised to the integral of p of t, which was, again, the coefficient function of y in the differential equation. And again, here, just to kind of keep in mind here, I'm not putting any bounds on this integral over here. Any particular antiderivative that we get out of here is fine. We don't need to worry about adding the constant of integration here. In our case, since t is greater than 0, we have that mu of t is going to be e raised to the integral of 3 over t dt. And the antiderivative of 3 over t is simply going to be 3 times the natural log of t. And again, t is greater than 0, so we can lose the absolute value bars over here. And using rules of logarithms, we're going to get that this is e to the natural log of t cubed, which is just t cubed. T cubed is our integrating factor. As it's a factor, we're going to multiply our equation 1 through by t cubed, and we end up with t cubed times y prime plus 3t squared y equals t times e to the negative t. The key here is that the left-hand side of this equation, equation 2 here, is simply the derivative of t cubed times y. And we can see this from the product rule over here very nicely. Now we're going to integrate both sides of that equation too. The left-hand side here is just going to end up to be t cubed times y. And here we're going to compute the indefinite integral of the right-hand side here. This follows by a quick little integration by parts, where if you like making those substitutions, the u would be t and the dv would be e to the negative t dt. And you can go from there. And we get the following. And to get our final general solution for y over here, we're simply going to divide through by t cubed, and we get the following here. And remember, our solution is only good for t greater than 0. So here is a portion of the direction field for this differential equation, equation 1, with the particular solution shown in yellow here, with that constant of integration equal to 14 times e to the negative 1. This also corresponded to like an initial condition where y of 1 was 12 times e to the negative 1. See that roughly right here. So to summarize, so the general method for solving a first order linear differential equation written out in this form over here follows the same process as illustrated in the example. We first find the integrating factor. So again, mu of t is going to be e raised to the integral of p of t. And the solution simply is going to be y equals 1 over mu of t times the integral here from u of s times g of s ds plus a constant of integration. These bounds over here, again, t here is really the variable of this function over here, and t naught here is conveniently chosen to be some value in the domain of our solution over here. Thank you.